Imagine taking a standard piece of graph paper that stretches out endlessly and folding it until that infinite grid fits inside a single circle. To understand why you'd ever need to bend space like this, we have to look at the physics of electrical transmission. When you send power from a source to a destination, you need every bit of that energy to reach the target. But wires have a property called impedance. If a signal traveling down a line hits a component with a different impedance, some of that energy bounces backward. It is exactly like flicking a thin rope tied to a thick one. The pulse hits the junction and snaps right back at you. These reflections are a disaster for communication. They create standing waves that distort data and prevent power from reaching an antenna. Engineers initially tried a standard Cartesian grid, plotting electrical resistance on one axis and reactance on the other. But electrical states can be infinite. To plot every possible circuit state, you'd need paper larger than any physical workspace. These early telephone engineers were effectively stuck. They could calculate small circuit sections using complex algebra, but they had no way to see the big picture of how different components interacted. Standard geometry was simply the wrong tool for the job. It couldn't capture the full range of electrical behavior in a format a human could actually use. By the 1920s, this was a crisis. The telephone industry built a massive, chaotic infrastructure, suffering from constant, crippling signal loss. Philip H. Smith, a young engineer at Bell Labs, realized making long-distance communication reliable required a mathematical transformation that didn't need infinite paper. He turned to conformal mapping, a mathematical technique that bends a flat plane while preserving intersecting angles. By dividing circuit L's by baseline impedance, called normalization, Smith pulled those infinite points toward a central origin. This wasn't a change in circuit physics, but a change in the coordinate system. By remapping the infinite plane into a circular space, the entire range of electrical possibilities could finally fit on a single page. As the transformation completes, the straight vertical grid lines curl inward, becoming a series of nested rings that cluster on the circle's right side. This creates a unique convergence point, representing infinity on the circle's edge. To eliminate reflections, you don't hunt endlessly. You add capacitors or inductors, physically navigating your circuit state along curved paths into the perfect zero-reflection center. The Smith chart turns the invisible behavior of radio waves into a navigable landscape, constraining the complexity of infinite values within a usable boundary. Even today, when computers can calculate a perfect impedance match in milliseconds, this hand-drawn chart remains a core part of an electrical engineer's training. A computer can provide a numerical answer, but it can't provide intuition. The chart allows engineers to see the why behind the numbers, showing the relationship between frequency, resistance, and reactance. Instead of guessing with algebraic formulas, the chart provides a spatial journey through the behavior of a circuit, showing exactly which direction to move to achieve a perfect match. The result is the seamless flow of energy we rely on, signals broadcasting across the globe without bouncing back or losing strength. The Smith chart survives because it takes the invisible, infinite behavior of electricity and renders it as a visible landscape the human mind can finally navigate.